Hi, and welcome to our presentation. This is Anthony Martinez, along with Ryan Conlon and Luke Procharka. Today, we'll be going over side channel attacks, what they are, what they do, and how hackers can take advantage of this to potentially leak sensitive information. So, what is a side channel attack? A side channel attack is a type of security exploit that uses information inadvertently leaked by system. This means hackers can steal your data without ever touching your files, cracking your password, or breaking into your system. There are many different types of side channel attacks, which we will get into later in this video. They all exploit hidden clues such as power, timing, and sound. In the top right, you will see a user who's being recorded by an eavesdropper who can potentially take this information, decode it, and leak sensitive information. In the bottom right, you'll see a machine's voltage being measured, be compared to the time in milliseconds, where users can figure out certain ways to potentially leak information as well. So the main objective of the side channel attack is to target the implementation side of a system via a side channel rather than conventionally its software or algorithms. So side channels include timing of operations, power consumption, electromagnetic emissions, sound, and cache usage. Hackers can leak sensitive information such as cryptographic keys, passwords, and private data. There are many different ways or reasons why attackers attack, whether it's to gain control of machines via botnets, to gain access to private information such as credit card numbers, to punish or embarrass individuals and institutions, like the situation in Sony by Sony in 2014, to educate and advocate on good community is Firesheep, who help just spread awareness about cybersecurity, or they could even just want it to earn reputation in the cracking community, and the list could go on. So how do you try to mitigate side channel attacks? The U.S. Department of Defense requires military electronics to meet Tempest-resistant standards. So chipset and operating system providers also provide software patches and updates worldwide, often before the attacks are well known by end user organizations. A great way to, again, mitigate side channel attacks is to use a Faraday cage to protect the most vulnerable data. So this could include introducing additional noise to a process to foil attacks, replacing traditional keycaps with those rubber keys in the top right, and adopting specialized software with the capability to protect data against side channel attacks. So you'll see those pictures. You can replace you can put a keyboard mat that will be over your keyboard to drown out the sound and also keep your keyboard clean as well. And in the bottom right is Scalib, a community that serves to protect against side channel attacks. They have their own GitHub, so you can look into that, but it's a software that you can download and install. So why do side channel attacks matter? Attacks have grown with the popularity of IoT devices, and the priorities for manufacturers for these devices are to create compact devices with low power consumption. Now, the drawback to this is that they do not focus on security, meaning there is less security in both the device hardware and the encryption software. Another thing is smart cards. So physical attacks can extract stored keys if protections are weak. If you look to the right, you'll see that when the chip is used, whenever you are purchase something at a store, the chip card antenna is placed, and then there's radio communication between the chip card antenna and chip module antenna. And lastly, one of the biggest concerns are shared cloud environments. So something popular through these shared environments is cache timing attacks, data leakage through shared resources, misconfigured cloud settings, for example, open storage buckets that can expose data. And lastly, insider threats from cloud provider personnel. So with all of the popular shared cloud environments like Azure, AWS, This is a big concern for companies where sensitive data can just easily be leaked.
Talking about is timing attacks. Timing attacks are a form of side channel attacks, and timing attacks work because computers do not always take the exact same amount of time to process different inputs. Every very tiny timing difference can give away useful information and clues to an attacker who is carefully measuring them. For example, if a password checker compares characters one at a time and stops when it finds a mismatch, a guess with more correct characters will take slightly longer to process. By repeating this process many times and analyzing the different timings, an attacker can slowly reconstruct the correct password or secret key. This shows that even something as simple as execution time can become a serious security vulnerability if it is not handled carefully. As we can see, some often targets of timing attacks are password checks, cryptographic operations, and login systems.
Measuring timing. We've explained that attackers can monitor the time it takes for an operation to execute, but how is this done? Modern processors keep a tally of how many clock cycles have elapsed since they were powered on. An attacker can write a program that reads this internal counter before and after an operation to see exactly how many cycles it took. In low-level assembly, the CPU provides instructions to read this data. In RISC-V, for example, a C program can embed the read cycle instruction. The attacker runs read cycle, saves the value, performs some arithmetic operation to access a specific memory address, and executes read cycle again. By subtracting the first timestamp from the second, the attacker knows exactly how many CPU cycles that memory action took. For example, if it took 2 cycles, the data was in a 1 cache. If it took 150 cycles, it was a cache miss. By doing this repeatedly across different memory addresses, the attacker is able to map out what the victim program is doing. To create this graph, researchers ran 1 million basic modular multiplications using the RSA reference software library. The mean of the graph is 1167.8 microseconds and the standard deviation is 12.01 microseconds. Different operations will have different timing distributions. Most of the work of determining which operations are happening comes down to complex statistical analysis.
Side channel attack that I'm going to talk about is power analysis attacks. In a power analysis attack, the attacker measures how much power a device uses while it performs encryption or another sensitive task. Even though the device is running a secure algorithm, different operations and data values can cause small variations in power consumption. These variations form patterns that can be recorded and analyzed. There are simpler forms like observing general patterns and more advanced methods that use statistical analysis over many runs to extract secrets. By studying these power patterns over time, attackers can sometimes recover encryption keys without ever directly accessing the data. Um, Often targets of this are smart cards, embedded devices, and hardware security modules.
Measuring power consumption. The attacker finds the power pin on the target chip. They cut the power trace and solder a resistor into the circuit. A small 50 ohm resistor is inserted in series with the power or ground input. The voltage difference across the resistor divided by the resistance yields the current. How is the data interpreted? The raw graph of power consumption is known as a trace. The x-axis represents time and the y-axis represents the voltage drop across the resistor, which corresponds directly to the electrical current being drawn by the processor. Different CPU instructions require different physical hardware to activate. An add instruction might use a simple ALU and draw a moderate amount of power, while a memory read might cause a sudden spike in power as the CPU reaches out to the RAM. Identifying data-dependent branching is one of the most important aspects of simple power analysis. For example, to decrypt data, RSA performs calculations on massive exponents using a secret binary key. The algorithm scans the secret key bit by bit, and if the current bit is 1, it also performs a multiply operation. If the current bit is 0, it skips the multiply and moves on. Because you can see the difference in the operations on the trace, you can begin to identify the individual bits of the secret key. On the upper graph, you can clearly identify 16 individual DES operations. On the lower graph, you can observe that the upper and lower traces diverge after the 6 clock cycle. The upper trace represents where a jump instruction was taken. The lower trace shows where the jump instruction was not taken.
The next thing I'm going to be talking about is acoustic and EM attacks. Some side channel attacks rely on signals that people normally ignore and wouldn't think much of. Electronic devices naturally emit electromagnetic radiation when they are operating, and with the right equipment, attackers can then capture and analyze these signals to learn about the computations that are being performed. Acoustic attacks work in a similar way, but instead of electromagnetic signals, they focus on sound. For example, the sound of keystrokes on a keyboard or simply subtle noises from a processor can sometimes be analyzed to recover sensitive information. These attacks highlight how even unintended physical byproducts of computation can still end up becoming security risks.
This type of acoustic attack is similar to the power monitoring attack because the signals intercepted come from the power delivery network. When a CPU executes intense cryptographic operations, its power consumption fluctuates wildly. The sudden massive shifts in current pass through the voltage regulator modules and capacitors. Due to the physical properties of these components, the fluctuating current causes them to rapidly expand and contract. This results in them vibrating, which creates a high frequency sound, which is often called coil whine. In highly controlled settings, attackers can use directional parabolic microphones placed a few meters away. However, researchers were able to prove that the microphone on a standard mobile phone placed next to the target computer is sensitive enough to capture the necessary frequencies. A raw recording of a computer running just sounds like static. To obtain usable data, the raw audio file is run through a fast Fourier transform, or FFT. The FFT converts the audio from the time domain, which is how loud the sound is at a given time, into the frequency domain, a spectrogram showing which pitches are present. But there's one issue still. The CPU runs at 3 GHz, or 3 billion operations per second, and the microphone only records at 48,000 samples per second. By the time the microphone captures a single frame of audio, the CPU has already executed 60,000 instructions. Luckily though, RSA algorithms do not execute a single problem and finish. They encrypt data by running a sequence of instructions through what is essentially a massive while loop, repeating the same operations thousands of times. If it enters a loop of 50,000 instructions, it will complete that loop in about 1 millisecond. Even though the individual instructions are a blur, the entire 1 millisecond loop has a distinct average power consumption profile.
Type of side channel attack I'm going to talk about is cache attacks. So, modern processors use caches to speed up performance by storing frequently accessed data in faster memory. However, this performance optimization can unintentionally create a side channel leak. If an attacker can observe which parts of the cache are being accessed, they may be able to infer what data or instructions a program is using. This is often done by measuring access times to different memory locations. Cache attacks are particularly dangerous in shared environments, such as cloud computing, where many or multiple users may be running programs on the same physical hardware. In those cases, one user could potentially learn sensitive information about another user's process.
Cache attacks rely on the attacker and the victim sharing some physical memory, which is common in cloud environments. Cache attacks focus on the L3 cache. Unlike the L1 or L2 caches, which are generally private to a single processor core, the L3 cache is shared across all cores on a modern CPU. This means an attacker can run run code on Core 1 and successfully spy on a victim running on Core 4 just by monitoring the shared memory space. Flush plus reload is a cache attack that allows an attacker to spy on the memory address access patterns of another program. The first step is to remove the data from the cache hierarchy, which is CL flush in x86. This data is pushed into slower main memory. The attacker then waits to give the victim process time to run its operations. If the victim process runs a path that needs that specific memory address, the CPU will fetch it from RAM and pull it back into the cache. At this point, the attacker will attempt to read that same memory address while using a timing instruction to measure how many clock cycles the read takes. If the read is fast, for example 40 clock cycles, the data was in the cache, proving the victim accessed that data. If the read is slow, 200 or more cycles, the data is still in the RAM. By repeating this process thousands of times a second, the attacker can trace the execution path of the victim's program and reconstruct cryptographic keys.
An example of a cache attack that actually happened is Spectre and Meltdown. So Spectre and Meltdown are some of the most important real-world side channel attacks. They didn't break encryption directly. Instead, they exploited how modern CPUs try to run faster using something called speculative execution. This is where the processor predicts and executes instructions ahead of time. Even though incorrect operations are supposed to be discarded, they still leave traces in the processor's cache. Attackers can measure those cache effects and use them to recover sensitive data like passwords or encryption keys. This was a major issue because it affected nearly all modern processors and forced companies to release security patches, often at the cost of reduced performance. It showed that even hardware level optimizations can introduce serious vulnerabilities.